My name is Robert Allen, and I'm a professor of climatology in the Department of Earth and Planetary Sciences. And I've been at UC Riverside for almost 14 years. It's basically a three-dimensional mathematical representation of the planet, where we kind of chop up Earth into these grid cells, both horizontally as well as vertically. And a climate model contains a representation of the major components of the climate system, including their interactions. This includes the atmosphere, the ocean, the land, and sea ice. These climate models are based on fundamental physical laws, including, for example, the laws of thermodynamics, conservation of energy, fundamental laws in fluid flow, such as the Navier-Stokes equations. These models are evaluated and rigorously tested against observations. So this includes, satellite observations, ground-based in situ observations, and overall, these models do very well at reproducing observed climatologies. So continued improvements in computational power, as well as investment in model development, have led to improved model resolution as well as model complexity. And these more complex climate models we call Earth system models. And these Earth system models include biological and chemical processes that can feed back onto the physics of the climate system. So examples are atmospheric chemistry and interactive vegetation. So climate models are useful for a variety of reasons, but they ultimately allow an understanding of the mechanisms driving climate change. And they also allow for the assessment of climate change impacts associated with both global and regional climate change. So these climate models are essentially a climate scientist's laboratory. They allow climate-related scientific hypotheses to be tested and evaluated. And this involves the design of controlled experiments whereby only one factor or a few select factors are varied. So this obviously is not possible to do in the real world because the target of these experiments is the planet, and obviously Earth is quite massive. Although ironically, human-induced climate change is essentially an example of a planetary scale experiment that we humans are conducting in the real world today. So in my research, I use climate models for a variety of reasons. For example, I use them to understand the climate impacts of atmospheric aerosols. So these aerosols are submicron particles suspended in the atmosphere, and examples include things like sulfate and black carbon. Anthropogenic aerosols are emitted into the atmosphere through a variety of human activities, including, for example, the incomplete combustion of fossil fuels. So aerosols are the dominant contributor to poor air quality, but they also have a net cooling effect on the climate system. Recent and future efforts to improve air quality through the reduction of these anthropogenic aerosols will unmask some of the greenhouse gas warming. Right? So this will accelerate global warming and exacerbate the associated climate change impacts. We want to improve air quality. It's good for human health, it's good for the environment, it's good for ecosystems, but pursuing aerosol emission reductions should happen with simultaneous reductions in greenhouse gases, right? This is the carbon dioxide, the methane, and nitrous oxide.